So at the end of the 1800s, physicists around the world were pretty certain that they could solve pretty much any physics problem they could figure out, they could even think of, right? With Newton's laws of motion and conservation of energy and conservation of momentum, they could solve pretty much any mechanics problem. And with James Clerk Maxwell's 4 equations of electricity and magnetism, they could solve pretty much any problem in electricity and magnetism. And then when they figured out that light, which is electromagnetic radiation, is really just oscillating electromagnetic fields, all sort of connected, they realized, or at least they thought they realized, that they could solve anything. And so at the end of the 1800s, they were just sort of celebrating, figuring, oh, physics is done. So they were just trying to solve as many different problems as they could. The issue was, at the end of the 1800s, they kept coming across some problems they couldn't solve, and they all seemed to involve light. At the end of the 1800s, the early 1900s. So we're going to go through a couple of those problems. The first of which is called atomic spectra. This idea that when gases absorb energy, they give off a characteristic spectrum, a unique spectrum that can actually be used to identify the individual gases, whether it's an element or a mixture of gases there. So this is the idea. In class we would demonstrate this using this device. You put a tube in here, and when you turn the switch on, it sends a current through the tube. So there's energy given to the gas particles, and then they release the energy back out as light. So it looks something like this. For example, when you put this particular element in there, it glows sort of this dullish, whitish blue. Here's different materials. This one is one you're probably most used to seeing. This is what neon would look like. This is basically a neon lamp, neon light. This is, I'm not sure which element this is, but in other words, the point is that they emit different colors. Here's another one that identifies what they are. So here's that neon, here's what helium looks like, here's what argon looks like, krypton, xenon. Each one has a characteristic, a unique spectrum. They didn't know why this happened. They couldn't figure out why every particular element and group of elements would give off a very particular spectrum of light. Okay, so that's the first one. Our second problem was black body, also known as thermal radiation. So when you hear thermal, of course, you're thinking heat. This is the idea that hot objects glow. And you've all experienced this anytime maybe you're getting breakfast ready in the morning and you put your bagel or your piece of bread in the toaster oven, and as it starts to heat up inside, you notice that there's the heating elements, a bar across. It starts off kind of gray, and as it starts to heat up, the first color turns is red. And then as it starts to glow hotter, it turns sort of an orangey. Or if you turn the burner on your stove, sometimes when the flame doesn't come on right away, or it just sort of settles in, it's first a little bit yellow, and then when it settles in, it turns blue. And so all this is the temperature increasing, right? And so it goes from red to orange to yellow, eventually to blue. What is happening to the frequency of the light as the temperature increases? Well, you probably remember that red is the low end of the frequency spectrum, blue and violet are the high end, and so as the temperature increases, the emitted frequency increases. And this is what they were noticing, that the hotter things were, the higher the frequency of the light that it radiated when it did so. And they're trying to figure out why this happened. So remember, we know that all light is produced by accelerating electric charges. So where are there charges accelerating inside, let's say, an atom? Well, think about the parts of the atom. There's the protons, neutrons, electrons, and electrons are moving around in circles. Circular motion is accelerated motion. So this makes sense, right? That the electrons are zipping around in circles, they're accelerating, they emit radiation as light. And so the idea was this, that there was an assumption that the frequency of the light was equal to the frequency of the electron. And make sure, of course, these are subscripts here, right? This is not flight, this is frequency of the light. This is not pholectron, this is frequency of the electron, right? The idea is that if the temperature increases, well, that means that the electrons are zipping around at a higher frequency, and so they give off a higher frequency of light. The frequency of light, the frequency of electron, this all seems to make sense. Okay, the problem occurred when they started taking data. So when they plot a graph of the intensity of the light versus the frequency, this is the pattern they always found, some sort of curve that looked like this. And if you recall, we've actually seen this before, back when we talked about the sun. The sun's spectrum has this, right? So low intensity in the low frequencies, low intensity in the high frequencies, it peaks somewhere in the middle, but all black bodies, all things that emit light when they glow, because they're hot, have a pattern like this. And the problem was when scientists tried to fit an equation that would map this out. And so using this assumption, the frequency of light equals the frequency of the electron, and whatever equation they could derive from this, they kept failing in trying to map an equation that would go to the data as well. One of the most successful versions looked something like this. It would go and go and go and follow the curve, and then all of a sudden it would just sharply deviate like this and just increase and never go over the curve like so. This sharp deviation occurred in the ultraviolet region. This came to be known as the ultraviolet catastrophe. Because of course, in physics, a catastrophe is when the data doesn't match an equation, right? A catastrophe in the regular world is a pandemic, right? Or a famine, or some horrible weather-related event, right? But in physics, if your data doesn't match the equation, well, then that is a career ender. That's a catastrophe. And so scientists around the world were trying to map an equation to the data. They couldn't get it to work until, in around 1900, a German physicist by the name of Max Planck, P-L-A-N-C-K, Planck, he figured it out. He discovered the correct equation that fit the data just about perfectly. Now, we're not going to get into the details of the equation. It's much beyond the scope of this course. But in his equation, he had to make an assumption. Here was the assumption. That when the electron changed energy, the change in energy was based on the frequency. This makes sense, right? Because when the electron changes its energy to a slower frequency, then it gives off a frequency of light that's matching that, everything's working, and then just some sort of constant here, which you just call lowercase h. But here's where it got weird, that the change in the energy was either hf, or twice hf, or 3 times hf, or some integer times hf, nhf. Okay, so why was this a problem? Well, let's look at a simulation here. Okay, so here I have a PHY simulation of a mass on a spring, and I'm going to pull it down, starting with some energy in the system. It's going to oscillate up and down. We can even track the energy on this graph over here. And you'll notice that there's a little bit of damping in the system. So this is a real-world system where there's some air resistance in the system, and as it oscillates, the spring itself will heat up. And so you can see that the energy in the system is decreasing. This is the energy lost to thermal radiation, in this case, heat, right? So things are heating up, and you can see the total energy in the system decreases. That happens every time. But you notice it happens in a very continuous manner. So the idea here is that the mass in the spring is supposed to represent the electron. The electron is zipping around at certain frequencies. The mass in the spring is oscillating up and down at a certain frequency, but in this sort of classical system, the energy is lost in a continuous way. And that was the thinking, that the electron should continually lose energy as light, as this mass in the spring does. But that's not what Planck was saying. Planck was saying that the energy should be lost in this chunk of hf, or twice hf, or 3 hf. So it wouldn't just so slowly lose energy. If I set this oscillating, it would oscillate for a bit and then just all of a sudden lose energy like that, with no reason or no mechanism showing why it should suddenly lose energy. You can see me, I'm clicking on it, sort of stopping where it is, but the idea is that Planck is saying that these electrons lose energy in a chunk like that, and not in a continuous way as it did before when the damping was on. And so here's the problem with Planck's model, is that the energy of the electron changes in what he called quanta, chunks, discrete amounts of energy, instead of this continuous way. If we're imagining the electron as being that mass on the spring, it should lose it in a continuous fashion as it emits light, but he's saying no, to make the equation work, it had to be in these lumps of energy, hf, or twice hf, or 3 hf, whatever that was. And he realized this was an error. It didn't seem to make sense. So he said to the physics community, he's like, guys, I'm sorry, I don't know what's going on here, but I have to imagine the electron loses energy in chunks, but the equation works. And everyone else in the world is like, hey, don't worry, Planck, you figure out an equation, it works, we'll figure out the other issues some other time. Okay, so that was what was going on with thermal radiation. The third type of problem concerning light was the photoelectric effect. Now, some of you may have heard of this before. We could really just sort of break it down by the word here. Photo refers to light, electric refers to electricity. Here's the idea, that when light shines on certain metals, electrons pop out. Okay, so that was what was going on here. You shine light on certain metals and electrons come out, which is electricity. And that was our third problem involving light. In the next video, we'll explore this one in a little more detail.